Section: Introduction. In this section, we discuss the significance of residual connections in modern neural networks, highlighting their role in stabilizing training and enhancing model performance. Since their introduction in the ResNet architecture, these connections have been widely utilized in various fields, including natural language processing, audio recognition, and computer vision. A residual neural network, or ResNet, is built by stacking layers called residual blocks. Each block follows a specific pattern where the output is the sum of a function applied to the input and the input itself. This structure allows information to flow more freely through the network. However, we note a potential drawback. Simply adding outputs from previous layers may dilute important information, as it treats all layers equally, which can lead to a loss of valuable data. To explore this dilution effect, we pose a critical question: can residual networks effectively learn to recover their input? This is a fundamental expectation for generative models. If our hypothesis about dilution holds true, we would expect a negative answer. To investigate, we designed a neural network with low rank layers and added residual connections to address the bottlenecks caused by these low ranks. We then compared this model to another that uses learnable residual connections, which we refer to as GRNV1. Our findings were surprising. The residual network struggled to reconstruct the input even after processing a large number of examples, while the model with learnable connections achieved much better results with significantly fewer examples. This indicates that ResNet does not adequately resolve bottlenecks, emphasizing the need for learnable residual weights to enhance model capacity. We introduced DeepCrossAttention, DCA, a new transformer architecture that builds on residual networks by using learnable, input-dependent weights to combine layer outputs dynamically. This allows the model to focus on the most relevant information and prevents information dilution. DCA also features depth-wise cross-attention, enabling richer interactions between layers at different depths without significantly increasing the number of parameters. DCA adapts the model architecture for each input token, optimizing the added parameters to effectively combine outputs from earlier residual blocks. This flexibility allows for various arrangements of residual blocks, enhancing performance without rigid architectural choices. We analyze our approach theoretically using a linear low-rank model, demonstrating that DCA achieves a better balance between accuracy and model size under certain conditions. We extend this analysis to nonlinear models and provide empirical results that support our theoretical insights. Our experiments in language modeling show that DCA consistently outperforms standard transformer architectures in terms of perplexity and training efficiency, while also improving training stability and reducing loss spikes. Section Summary. In this section, we discuss the significance of residual connections in neural networks, highlighting their role in stabilizing training and improving convergence. We introduce our proposed architecture, DeepCrossAttention, DCA, which utilizes learnable, input-dependent weights to dynamically combine layer outputs, thereby preventing information dilution and enhancing model performance, particularly in language modeling tasks. Section: Related work. In this section, we discuss related work that has influenced our approach. We note that residual connections have allowed information to flow directly from earlier to later layers, which has been essential for stabilizing training and enabling the creation of deeper networks. DenseNet further improved this by combining outputs from all previous layers into each layer's input. Several methods similar to ours build on DenseNet but use efficient ways to aggregate outputs instead of concatenating them. For instance, DenseFormer performs aggregation through a learned linear combination of previous outputs and reduces computational demands by applying this only to a subset of layer connections. Laurel, which builds on DenseFormer, introduces 3 aggregation functions, with the most effective one applying a learned low-rank transformation before the linear combination. Another approach, hyperconnections, uses a fixed-size stack where outputs from layers are added with learned weights for each stack slot. Before each layer, the stack is mixed using a learned weight matrix, and the layer input is derived from a learned linear combination of the stack, rather than directly from previous outputs. They also propose a dynamic version where weights depend on the inputs. Next, we present our generalizations to the residual network architecture, introducing 3 proposals that progressively increase the network's complexity. From these proposals, we develop DeepCrossAttention, DCA, a new method to enhance the residual learning capabilities of the transformer architecture. We define a residual function for each layer, where the output of a layer is recursively defined based on the outputs of previous layers. We also describe a stack of layer outputs, which helps us express our generalizations. Our first generalization, GRNV1, uses simple linear combinations of previous outputs with dimension-independent weights. The second, GRNV2, allows for dimension-dependent weights, using different weight vectors for different features. The third, GRNV3, introduces input-dependent weights, combining dimension-dependent weights with a nonlinear mapping of the input features. To address memory and computational efficiency, we note that the stack of outputs grows with model depth, which can be burdensome. Our experiments show that GRNs tend to prioritize inputs and outputs from the last few layers. Therefore, we propose including only the first and last few layers in the stack, while applying standard ResNet operations to the intermediate layers. For example, if we include 2 layers, the stack would consist of the model inputs, the sum of intermediate outputs, and the outputs from the last 2 layers. This modified stack serves as input for the GRNs. Section Summary. In this section, we review advancements in residual networks, highlighting how methods like DenseFormer and Laurel improve information flow through efficient aggregation of layer outputs. We then introduce our generalized residual networks, GRN, which utilize weighted linear combinations of previous layer outputs to enhance model performance while addressing memory and computational efficiency. Section: DeepCrossAttention. In this section, we describe our main method, which is tailored for the transformer architecture. We introduce DeepCrossAttention, DCA, which enhances self-attention by incorporating 3 separate instances of a generalized residual network, GRN, in each decoder block, specifically using GRNV3. These 3 GRN instances receive the same inputs from the previous layer and produce the queries, keys, and values needed for the attention mechanism. This setup allows for more complex interactions between layers at different depths. We illustrate this with a diagram of a DCA decoder block within a transformer, where the skip connections ensure that the inputs are not directly added to the outputs of the decoder block but are included in the inputs for both the attention and feed-forward modules. Importantly, DCA does not change the fundamental attention mechanism. Instead, it utilizes GRNs to dynamically create the inputs for attention. Next, we focus on the theoretical analysis, particularly in the context of language modeling tasks. We examine scenarios where the training set size significantly surpasses the input dimension. As we increase the number of model parameters, the network's ability to represent information improves, which helps lower the test error. We will analyze the balance between test error and the number of parameters, arguing that our generalizations provide a better balance compared to standard ResNet. We begin by exploring a simplified low-rank linear model to understand the relationship between test error and model complexity, highlighting the advantages of our proposed generalizations. Our analysis clarifies how various factors, such as the collective widths of layers, the complexity of the target task, and the input dimension, influence this trade-off. We will also discuss how some findings can be applied to nonlinear models and provide empirical evidence that supports the relevance of our insights for more complex models. Due to space limitations, we will include the proofs of our theorems in the supplementary material. In our low-rank linear model, we consider a scenario where each sample's response is determined by a matrix multiplied by the input plus some noise. We analyze a network with multiple layers, defining the rank of each layer and the total rank across all layers. We will compare 4 architectures: Baseline, ResNet, GRNV1, and GRNV2, each with T layers, and describe the types of functions each can represent. For the baseline architecture, without residual connections, the model is represented as a product of matrices applied to the input. For ResNet, we include identity connections, allowing for a different representation. In grnv1, we express the output as a function of a vector, while in grnv2, we use a matrix to represent the output. We summarize the capabilities of each architecture in terms of the rank constraints on the matrices involved. Section Summary. In this section, we introduce DeepCrossAttention, DCA, which enhances the transformer architecture by incorporating 3 independent grnv3 instances in each decoder block to improve layer interactions without altering the attention mechanism. We also analyze the trade-off between test error and model complexity, demonstrating that our generalizations outperform standard ResNet architectures in this regard. Section: Trade-off between test error and model complexity. In this section, we explore the balance between the best test error we can achieve with different models and the complexity of those models, which we define by the number of parameters they have. We note that all the models we discussed earlier are linear functions. For a linear model that maps input X to an output using a matrix A, the test error, or model risk, can be calculated under the assumption that the expected value of the product of X and its transpose is the identity matrix, indicating isotropic features. Since the constant term in our error calculation does not depend on the model, we will ignore it and focus on the excess risk instead. We denote the minimum excess risk for a class of models C as the smallest difference between the true model A and the approximated model A hat, measured in terms of the Frobenius norm. The best excess risk for a basic model class is achieved through the best R-rank approximation of A, while for a residual model class, it comes from the best RT-rank approximation of A minus the identity matrix. Both of these can be easily characterized using the singular values of A and A minus the identity, thanks to the well-known Eckert-Young-Mirsky theorem. Finding the minimum excess risk for the grnv1 and genb model classes is more complex, so we will establish upper limits for these in the next theorem. We consider the singular value decomposition of A minus the identity and define a new term that represents the difference between A minus the identity and its best R-rank approximation. Next, we analyze the model complexity for each architecture based on the number of parameters. For ResNet, the number of parameters is twice the product of D and R star. For grnv1, it is twice the product of D and R star plus a term related to T, and for grnv2, it includes an additional term involving D and T. We observe that if grnv1 and grnv2 show a better trade-off between excess risk and model size compared to ResNet, we can enhance this advantage by scaling the difference term. In the following theorem, we will focus on grnv1 and grnv2, providing conditions under which they outperform ResNet in terms of excess risk relative to model size. We will also establish a lower bound on the improvement in excess risk that grnv1 and grnv2 can achieve over ResNet while using the same number of parameters. We assume that the difference A minus the identity is positive semi-definite and define the maximum and minimum eigenvalues of this difference. We then consider a ResNet model with a collective rank defined as the sum of the ranks across T layers. We find that if certain conditions are met, grnv1 and grnv2 can achieve a better trade-off compared to ResNet. We define two terms that represent the reduction in optimal excess risk for grnv1 and grnv2 compared to ResNet. Finally, we quantitatively demonstrate how grns can reduce the collective rank while maintaining the same test error as ResNet. Specifically, if we have a ResNet with a collective rank less than D, a grnv1 or grnv2 model can achieve a smaller test error with a reduced collective rank. Section Summary. In this section, we analyze the trade-off between test error and model complexity for various architectures, focusing on how the optimal excess risk relates to the number of parameters in linear models. We establish that grnv1 and grnv2 can achieve better excess risk model size trade-offs compared to ResNet, allowing for reduced test error with fewer parameters under certain conditions. Section: Insights from the analysis. In this section, we analyze the insights gained from our findings. The theorem helps us understand how various factors influence the performance of generative recurrent networks, GRNs. First, we consider the complexity of the target task, represented by a value we call kappa, which ranges from 0 to 1. As kappa decreases, the associated matrix becomes more like a low-rank matrix, making it easier for low-rank models to learn. We notice that the thresholds for performance increase with kappa, indicating that for more complex tasks, GRNs can outperform the trade-off achieved by ResNet over a broader range of collective ranks. Additionally, for a specific task with a fixed kappa, if the collective rank exceeds a certain threshold, ResNet is already sufficiently capable, making further improvements challenging. Next, we look at the collective rank itself. The lower bounds on the gains we observe decrease as the collective rank of ResNet becomes smaller. This suggests that as the collective rank diminishes, the information dilution in ResNet increases, allowing GRNs to enhance model performance with the same number of parameters. We also examine the role of input dimension. The upper bounds on the collective rank increase with the input dimension, and the lower bounds on the gains also rise with larger dimensions. This means that with higher input dimensions, GRNs can outperform ResNet over a wider range of collective ranks and achieve greater reductions in model error. We refer to a figure for a visual representation of these trends. Finally, we extend our discussion to nonlinear models. We define bottleneck rank, which is the smallest integer indicating how a function can be factored into two parts with a specific inner dimension. This concept is closely related to the Jacobian rank of a function. Generally, the Jacobian rank is less than or equal to the bottleneck rank, but for certain functions, they are equal. We also outline properties of these ranks and consider a multilayer perceptron, MLP, to illustrate our points, defining the collective rank of the network and various subsets of functions based on their bottleneck ranks. Section Summary. In this section, we analyze how various factors, such as target task complexity, collective rank, and input dimension, influence the performance of generative recurrent networks, GRNs, compared to ResNet. We find that lower task complexity and collective rank enhance GRN's ability to reduce model error, while larger input dimensions provide a broader range for GRNs to outperform ResNet, ultimately leading to improved model performance. Section: Experiments. In this section, we conduct experiments on language modeling tasks to assess the effectiveness of DCA and confirm our theoretical insights. We compare DCA's performance against the standard transformer on the LM1B and C4 datasets. Each model has an embedding dimension of 512 and an MLP dimension that is 4 times the embedding dimension. By default, DCA uses outputs from all previous layers as input to the GRNs. When we only include the first and last K-layer outputs in the input stack, we refer to this as KDCA. Each model is trained with a sequence length of 128 and a batch size of 2048 over 64 TPUs for 500,000 steps, totaling 131 billion tokens. We utilize the ADAM-W optimizer with specific parameters for beta values, weight decay, learning rate, warm-up steps, and an inverse square root schedule. In our first experiment, we pre-trained both a transformer and DCA on LM1B, increasing the model depth from 6 to 42 layers. We observe that DCA achieves lower perplexity for a given number of parameters, with the 30-layer DCA model outperforming the 42-layer transformer, indicating that DCA is more parameter efficient. We also explore the efficiency of DCA by including only the first and last K-layer outputs in the input stack. Our findings show that reducing K speeds up training with only a slight increase in perplexity. Both small and large K values yield good training efficiency, allowing DCA to reach the final perplexity of the transformer in a third of the time. Setting K to 2 results in a model with 48% lower inference latency compared to K set to 24, demonstrating that a smaller K leads to efficient training and faster inference. Next, we analyze the training time efficiency of our model architecture. We present the training time versus perplexity trade-off for various layer configurations. The results indicate that 2DCA achieves better perplexity for a given training time, showcasing DCA's training efficiency. We then examine model width scaling, validating our theoretical results by varying the model width. Our findings reveal that the benefits of DCA decrease as the model width increases, consistent with our theoretical predictions, while improvements in depth scaling are maintained for deeper models. In another experiment, we trained Transformer and 8 DCA models of increasing size on the C4 dataset. The results consistently show that DCA outperforms the standard Transformer, although the absolute improvement in perplexity diminishes for larger models. We also investigate retrofitting pre-trained models. Since our method resembles a standard residual network at initialization, adding DCA to a pre-trained model does not change its function. We find that incorporating DCA leads to a perplexity improvement of 0.23 after additional training steps, compared to just 0.015 for the Transformer. Regarding training stability, we observe that loss spikes can disrupt training for large models. Our results show that DCA training is more stable, with no significant loss spikes, which is a notable advantage. Finally, we compare DCA's perplexity with recent related works and find that DCA improves upon the previous best method, hyperconnections, by a significant margin. In our ablation study, we analyze the relative gains of each proposed generalization, revealing that the largest improvement in perplexity comes from GRNV1, followed by DCA and GRNV2.